Okay, we are recording. So then let me hand over the presentation to group 243D, the traumatized kids that are going to present Gerald.
Alrighty. Good evening, everyone. Thank you for coming today. Thank you, Dr. Trump, for that transition. Thank you for coming to the presentation of Group 243D, otherwise known as Traumatized Kids. We'll be presenting to you G.E.R.A.L.D. G.E.R.A.L.D is essentially a grounded, electronic, reliable, autonomous laser deflector, our heliostat design, essentially. But before we begin and I get into a little bit more about our design and what inspired us, I'd like to introduce the team. First off, Christian Hooker, Daniil Kardashov, Benjamin Lehman, Brooke Olson, Joshua Owens, Joseph Rios, and myself, Abraham Sheikh. So moving forward with our first off is our Hedgehog Concept. There's three main pillars of this Hedgehog Concept. It's the easy accessibility, the straightforward design, low manufacturing assembly costs. These three things are actually the biggest things what moved us towards designing our heliostat and choosing certain components for it. Easy accessibility or easily accessible is a very important concept to us in regards to the fact that we want this heliostat to be very, I guess, easy of use, have an ease of use towards changing parts, whether it were to break or just quickly be able to just replace certain parts, certain aspects of the heliostat as quickly as possible. So there's low downtime and we can get the most solar output as possible, as much as possible. Secondly, straightforward design. We want this essentially heliostat to be something that's not some complex monstrosity in terms of directing sunlight towards a solar tower, but simply something that anyone can look at, have an intuitive design, can possibly take apart if necessary, and rebuild as quickly as possible. Third, but not least, the low manufacturing assembly costs. That is a really crucial and important step in our entire design, especially because we are at a design constraint where we have to focus on $100 per area of reflective surface. And so we tried achieving that through using 3D printing, pay attention to the cost of like fasteners or any type of fasteners or epoxies that we use, because that quickly adds up very quickly. And essentially the type of motors we are using at the end of the day and the control module. So moving forward with our entire design, we can see that we have several subsystems: a mirror subsystem, an actuation subsystem, electronics, and a base subsystem. Not in this picture is actually a shroud that goes over the entire heliostat design itself. Essentially, that shroud basically protects the entire internal components. As you can see, there's a breadboard electronic motor controller, and then a power supply. So the shroud essentially protects all of that. And we use basically, I guess, banjo clips or something to just screw them together and hold it and fasten it in place. So now I'll be transitioning you over to my associate, Benjamin Lehman, to explain more about the heliostat design. Thank you.
Hey guys. So for design highlights and key features, a few things make us stand out from the other groups. This includes our compact design. All of the hardware required to run each heliostat is contained within the protective duct or shroud that Abe had mentioned on G.E.R.A.L.D's exterior. The heliostat is also lighter, using 3D printed material instead of other materials that would take more time and money to manufacture. G.E.R.A.L.D's azimuth and elevation gears make the overall system easier for assembly and make the system less code intensive for operation. In conjunction with this, the smaller motor used in the elevation motion creates a less top-heavy design. And all of these features are contained within G.E.R.A.L.D's protective duct, which provides weather protection from the elements and protection from things such as dust and water. It also can be easily removed to access G.E.R.A.L.D's simple internals. When we decided on a design to work with, we had to make adjustments right at the start to ensure the heliostat would be functional as a prototype. The elevation gear used was redesigned to make the gear mesh external instead of internal, which would provide uniformity between the axes and increase range of motion. If you look over to the right-hand side of the slide, you can see this original design with the internal gear mesh. And in addition to this, the mirror mount was changed to adhesive to reduce the amount of reflective surface taken by fasteners. You can see this as well if you look over to the right-hand side of the slide and over towards the bottom. Lastly, a protective duct was added to so that the base and the mirror subsystems were modified to accommodate that as well. If you guys remember in previous slides that Abe told us about or had shown us, you can see the heliostat without its protective duct. And at the top where the mirror is, it's circular, and at the bottom of the base, it's circular as well, and that's where that duct will mount up. So over the course of the heliostat's prototyping, a few changes were made to improve performance. We first replaced the elevation motor with a smaller unit because of the weight that it added up higher on the heliostat, and because the larger motor had more power than we really needed. Counterweights were also added to balance out the elevation motor so that the azimuth motor would perform in tests such as the laser test, or help it perform better in those situations. The H-bridge also underwent 4 redesigns, and these revisions were made to keep G.E.R.A.L.D operational throughout the prototyping process. We also added labels to the heliostat so that we could make quick work of testing and keep input straight when using the code for operating it. The electrical box was omitted from the design due to electrical parts being housed within G.E.R.A.L.D shroud that was mentioned earlier in previous slides. And lastly, the front face was redesigned to reduce weight by hollowing out the area around the hose clamp, or the area where the hose clamp attaches the shroud to it. And the front face became 4 separate pieces due to printer limitations, but it could be made into one piece if the heliostat was to be produced at a larger scale. And so with that, I'd like to hand things off to my friend Josh.
All right, thank you, Ben. So as mentioned, the most adjustments were made to that H-bridge piece, since that's really the heart of our motion system. So our first iteration, it's shown there in blue, mistakenly printed with 100% infill. And while that was okay for some of the other parts, that ended up being massively too heavy to be moved smoothly by our stepper motors. So that was really where we discovered that weight's going to be a big limiting factor in the performance of our design. Also, the geometry of those vertical mounting tabs interfered a lot with the mirror mounting surface, so that limited our range of motion within a range that wasn't adequate for our testing. So you can see there that we've made an effort to file down the faces to get a little bit more motion out of it. Overall, a very crude design and needed a lot of work. So for our second iteration there in silver, we were much smarter with our print settings, opting for 15% infill this time. And that maintained more than sufficient rigidity, and it cut out a significant amount of weight and material. So to further the weight reduction, then we added those hexagonal cutouts and reshaped those hinges a bit for better clearance and less material. So after all of those changes, we ended up reducing the weight by nearly 70%. That was huge for performance and for print times as well. So then our third iteration there in purple was after we started testing and realized that the positions of our limit switches weren't going to work out with those cutouts. So for that one, we just eliminated a few of those holes, and it performed as needed for those tests. So then, of course, for all of these, though, we were constantly updating tolerances, adjusting very small things to help ease of printing and also ease of assembly and smooth motion. So getting to our final iteration, this is what we developed really toward the end after we had gotten a lot of testing done. It wasn't really until that point that we realized the gear teeth were actually a big limitation in our performance. The first designs were using a very large tooth, and that allowed for a lot of play in the gear mesh. So when we would go to move to a specific position, there was a good deal of uncertainty in where that would actually end up. So with the final redesign here, we switched to 32 pitch teeth. That increases our points of contact and reduces the amount of uncertainty in positioning. Unfortunately, though, we do lose gear reduction in that process because we needed to keep the diameters roughly the same to avoid redesigning the rest of the parts. And so we made the choice to use microstepping. With the controllers we've picked out, we have the option to use no microsteps, 4, 8, or 16. And with each of those processes, you lose a little bit of torque. So we settled with 4 microsteps. With that change, we were able to get the resolution of our movements down to 0.16 degrees per step and still maintained adequate torque. Another benefit of that design was just much smoother and quieter motion out of those motors. So here's the final H-bridge design in practice. Really, the main selling point of this part is that it combines three big features into a single piece. We have that front spur gear that allows for movement in the azimuth direction. And then we have a motor mount integrated into the rear for controlling the elevation. And we also have those vertical mounting tabs to attach the mirror mounting surface and elevation surface. So since all of those features are built into one piece, we reduce the assembly time, and we're also increasing the strength of that piece because we've avoided the need for extra hardware or adhesives that would be needed to hold multiple parts together. So then to complete it all and attach that to our base, all you need is a single bolt and lock nut, and that can be easily attached or removed. So all of those changes were made easily possible thanks to 3D printing that we relied on heavily for this whole project. So I'll let Christian continue with that and more on our subsystems.
Thank you, Josh. As far as fabrication of parts goes, our design relied heavily on 3D printing. So besides the electronics and fasteners, most parts were 3D printed, including the base, the pole, the interlocking front face mirror backing, and the main components of the actuation system shown here on the print bed. The base and pole are printed with 100% infill, while the other parts I mentioned are printed with 15% infill for weight reduction. And all 3D printed parts will be injection molded for mass production. One main subassembly is the mirror subassembly, and this subassembly uses the interlocking front face, which incorporates the replacement divots for placing the 6x6 mirror, as well as a ridge to secure the protective duct work, the duct hose. So the mirror is mounted to the interlocking front face via adhesive. Next, the actuation system consists primarily of the H-bridge, and this is mounted around the H-bridge are the azimuth and elevation motors, as well as the gears to drive the two axes of motion. The motion is derived from gear-to-gear contacts, with both gear ratios being 2.9. As far as the range in the azimuth axes, we have 150 degrees, while the range in the elevation axis is 60 degrees. And for our motion, our actuation is on the azimuth motor is a NEMA 17 stepper motor, while on the elevation motor, we use a short body NEMA 17 stepper motor for weight reduction, as the NEMA 17 motor for the azimuth struggled to actuate the H-bridge section, as well as the motor when in the worst case configuration at max angle. Now I'll pass it off to Joseph to talk more about the base subsystem.
Thank you, Christian. So last up, we have the base subsystem as seen from the bottom and slanted backwards. This features the protective duct around the model, a 3D printed shaft, and a 3D printed base with a built-in testing mount attachment, as well as a ridge to fit the protective duct. The testing attachment is temporary. It was designed to fit lab testing restrictions. The duct is to prevent exterior particles from interfering with our heliostat and to also cover exposed gears, acting as a safety function. Note that the shaft has cutouts built in for printing to allow the motor to be inserted and mounted. Additionally, the hole cut out of the bottom is to allow for the power cord to be inserted into the design. A notable modification added to the design was the replacement of the NEMA 17 motor with a smaller version. The larger motor has a rated torque of 0.45 Newton meters with a mass of 0.28 kilograms, compared to the smaller motor having a rating of 0.16 Newton meters with a mass of 0.041 kilograms. The top plate assembly has a mass of approximately 0.25 kilograms, and applying that to the center of mass of the symmetrical top part is 0.0605 meters away from the motor, yields a max torque of 0.1484 Newton meters. This falls within the acceptable limits and trades off 1/10 of the weight for 1/3 of the torque. And here are our three primary subsystems shown in exploded views. As seen, the actuation subsystem has two small bearings that are put in pre-made holes on the H-bridge to allow ease of rotation. This process is repeated in the mirror subsystem to the two attached flaps, the printed driven gear, and the rectangle. The smaller motor attaches to the printed motor mount, and rotation is controlled via partial threaded fasteners with lock nuts on the ends to secure them in place. With a base subsystem, the AC vent goes over the entire design, fitting in the grooves of the top plate and the base plate with the help of vent fittings on both. Finally, we have the mirror subsystem, which is designed in a sort of puzzle structure as a result of the Wertheim lab being busy with prints and the printers in the Mech 3 lab not being large enough to produce the full part. In the future, it will be more beneficial to print it as one part for this design. As seen, the manufacturing is essentially just putting 4 primary 3D printed parts together with fasteners, so the manufacturing cost is estimated to be 0 as a result. And now here we have Daniil with the prototype testing.
All right, thank you, Joseph. The prototype passed all test requirements set forward for it. The wind test is shown on the left here. It consisted of the prototype being rotated on the pedestal while being subjected to wind blown by a box fan, which is not shown here, and a leaf blower, which is pictured on the left. The tracking test is shown to the right, and it required the prototype to successfully redirect a laser beam to a target on the wall, which we were given coordinates for. The laser was aimed perpendicular to the ground, aligned with the center post of the heliostat, and the mirror was to be rotated to redirect the laser to the required targets. This slide contains a video of the wind survivability test. This test does not strictly represent the conditions that the heliostat would undergo in real operation, but rather serves as a milestone that ensures the heliostat can withstand basic wind gusts. This slide shows a video of our prototype performing for the laser targeting test. There were some difficulties in the calibration of the laser due to the inconsistency of the setup, but with proper recalibration, we were able to hit the target consistently within the red zone or within 1 degree of the target. So for the targeting of the heliostat, the azimuth angle alpha and the elevation angle epsilon needed to be calculated. Angles alpha and epsilon were calculated based on target location coordinates A, B, C, and the heliostat height, in the heliostat base centered coordinate system, and the heliostat height H. This was achieved using rotation matrices for transforming an arbitrarily reflected laser beam and setting that equal to the target position vector, operating under the assumption that the ray that needed to be reflected was pointing straight down. The acquired angle equations are shown here on the right. These equations were later subjected to a calibration due to imperfections in the system. This calibration is specific to each station that the heliostat was tested on, so they're not shown. And it was a linear calibration. And now I'll pass it off to Brooke for our cost summary.
Thank you. I would like to walk you through the price estimations for a single heliostat, starting with the lab cost and working up to the bulk cost. The lab cost for one module is $26.09. This is comprised of the products purchased for the prototype that were not already provided in the lab. This includes fasteners, protective ducts, smaller motor, counterweights, and bearings. The manufacturing and assembly labor is $0 because we performed those tasks in class and we're not paid to do so. The energy consumption was also provided to us. Next is the prototype cost for a single module is $171.42. And this is the total to build one prototype. This includes the cost of items such as filament, mirrors, motor drivers, limit switches, and other electrical components. These parts were purchased from retail stores, so the prices are expected to be higher than the bulk estimates. The raw materials is the amount of filament used for 3D printing at 15% infill. The manufacturing cost is the process for a machine to set up and hand remove the materials from the 3D prints for our main components. These costs were found using the unit cost for performing manufacturing processes, and that was given to us. The assembly labor is based off the Boothroyd and Dewhurst charts, which assumes the parts are to be assembled in an assembly line. Thus, we doubled the assembly costs for the prototype to account for the lack of assembly line and assembling inside the lab. Energy consumptions cost is defined as the energy consumption for a single heliostat operating the entire day for 1 month. This was found to be insignificant because the estimation was less than a cent. Moving on to the bulk cost, we found that to be $127.18. This estimate is based on the assumption of ordering enough supplies to build 3,000 modules. The OTS parts were estimated to cost 30% less than the prototype costs. This percentage was found from averaging the percentages from a few manufacturing pricing resources I found. Unlike the prototype, which is 3D printed, the raw materials used for the bulk manufacturing is composed of injection molded parts. We chose to injection mold our parts because it was cheaper than using other materials, it's more durable than 3D printing, and more accessible in the manufacturing workplace. The manufacturing labor is $0 because there is not a true raw material for the bulk cost. The injection molds are completed out of house and shipped to us ready to assemble. The only manufacturing cost we would have is if we wanted to buy a large mirror and cut it to size. That cost would be an additional $2.29 per module for cutting and setting it up. We don't plan to do this because it is cheaper to order and pre-cut mirrors because of their small size. It should take approximately 13.5 minutes to assemble each module using the Boothroyd-Dewhurst charts. This estimate accounted for worker salaries to be based on the average hourly pay for non-skilled manufacturing workers, with additional pay for benefits and overhead costs. As mentioned previously, energy consumption costs are insignificant when estimating a single heliostat, although we estimated the cost for operating 3,000 modules in Las Vegas, Nevada per month, and that would cost 37 cents. So as seen in previous slides, we know that our design is tested and proven to meet all the needs for our buyers. It's cost efficient and can be implemented with a minimal manufacturing time. Given our focus on a simple and compact design, we were able to offer a heliostat that is lightweight, protected from the environment, easily assembled, and is simple to maintain. Our design is ready to be further progressed to be mass manufactured. I just want to give a quick thanks for coming to our presentation and a big thank you to Cummins, Northrop Grumman, Carrier, Arrigo for sponsoring us. If you have any questions, you may ask them now.
So feel free to drop any questions in the chat. We'll do our best to get to those as well.
So I don't normally ask questions, but I just want to ask one real quick is you guys initially had the flexible bellows shroud around your heliostat to keep it protected from, dust and water and stuff. But then in your laser test, you removed it. So is that, yeah, there you go. Is that going to impact your accuracy, having to move the motors against, whatever rigidity that thing creates?
I'll take this one. So this was a very late realization, but the impact of the duct was much more significant than we were originally expecting. And because we opted for a smaller motor on the elevation axis, it did not have enough torque to accurately move it for the laser test. To counteract that, we'll most likely have to switch back to the older large motor because it has a much higher torque rating. And then we'll have to go through a little bit extra work to counterbalance it properly. Just because of the design of that H-bridge, all of the weight from the motor is centered on one side, and the azimuth motor doesn't have enough torque to move it back in the other direction. So with a little bit more balancing and a little bit more time to work on that, we could have implemented the duct for the laser testing as well. It just sort of goes back to the original weight issues that we were running into with those selected motors.
Got it. All right, thanks. Okay, so sorry to monopolize things. Let me ask if any of our panelists have questions.
Actually, oh, go ahead.
No, go ahead.
If you wouldn't mind, could you go back to the cost slide? Perfect. Okay, so let me just start off with, y'all couldn't see because my screen was off, but the giant smile I had on my face when y'all address manufacturing and labor and assembly labor costs. I've hounded on pretty much every single team so far today for people not considering that, because that, I mean, as you can see, it's not a little amount, you know, $10, $11, $12, especially when you start making 3,000, very much adds up. So thank you so much for addressing that. If looking at this from an investor side, that's the first thing I notice is the costs. Other than that, I will not comment on the engineering, because if any of y'all watched my lectures in the past, I'm not an engineer. But from, again, kind of, I take the investor's perspective. The fact that y'all are all dressed very nicely, all of your backgrounds look the same, you know, the sound quality is very good on your Zooms, the whole 9 yards. You present yourselves in a very professional manner, and that really does help me as an investor feel like you have your stuff together. So kudos to you guys. Very, very good. You're the only team so far that I've not had negative feedback on. So good job.
Thank you very much.
Thank
Joey.
you.
Thank you so much.
This is Rick Miles from Northrop Grumman. So I like the concept of the sleeve, but from an aesthetic standpoint, right, it doesn't grab you as something you would want to. So I would just recommend, if you go forward with the sleeve, I know that, you know, it's just a ducting type sleeve there. Maybe think of a different way to fix it than a typical duct type tightener, right? Maybe some clips or something on it, just something that makes it a little bit more aesthetically pleasing from someone wanting to purchase it, right? I really enjoyed the explanation of the evolution of the H-bridge design. I thought that was very well done. And then there was a slide where you mentioned a 1/10 to 1/3. If you could go to that slide. Want to make sure I understand. Yeah, so you said almost a 1/10. Was it a 10% reduction or a 90% reduction in weight?
Joseph, you want to take that one?
Yeah, I was just looking at it. Yeah, you're right. It's 90%.
Yeah, I just think a 90% reduction sounds a whole lot more impressive than
Yeah.
you're reducing it by a factor of 10, right? Just the way you say it on the slide, I think more of a salesmanship sort of thing. You know, you went and reduced the weight by 90%, and that still your only loss was a third in torque. I think that sounds a lot more impressive. So, but other than that, I thought you guys did a really good job.
Awesome. Thank you so much.
Thank you.
Okay, any more questions from our panel? Nope.
I would like to say one more thing, just because Dr. Brooks is here. As Daniil talked about during the semester, he was our code and programming master. This whole project really gave us a good appreciation for closed loop control. Trying to make the heliostat hit those targets without any sort of feedback was actually very difficult. Manually going in, calibrating, just repeating tests over and over. That was a frustrating process at times. So a potential improvement that we can make in the future is using different motors that give us some sort of position feedback, and using that to aid in our calibration process.
Yeah, that feedback really do be, so important. So you get to see it in real time, or maybe slow real time over the course of weeks of why it's so valuable to have that feedback so you can automatically, do all that. Because actually you were doing closed loop control, you're just doing like the really caveman kind.
Sure.
Where you tried out a thing and then you used your eyes as a human and you're like, oh, I didn't make it, and then you went and changed stuff. And the beauty of controls is that we can automate it with logic, but it's expensive. You gotta have the sensors.
I heard that you guys were using limit switches, and the initialization process and then the calibration process is very sensitive to the limit switches and how you begin and what you call the angle when you come off the limit switch in your code. So you guys wrote the software for this as well?
We did. Daniil, you want to take
Yeah.
that one?
Yeah, we wrote the code and it was just a set angle that it bounces off the limit switch.
But it's very sensitive to the kind of limit switch you have and the
yeah, it was-
consistency of that.
It was very sensitive. That was one of the parts that we were trying to combat and try to minimize the uncertainty from that. But yeah, the homing was a big source of uncertainty.
Maybe what you could do is just home it and then keep it powered overnight. You know what I mean? Keep it powered for subsequent testing.
We were very, very close to that.
Right. Awesome job, guys.
Thank you.
Thank you.
Very well done. Okay. We might have time for one more question. We're running a little over, but we should be okay if there's one more question from the panel. No. Okay. All right. I think we're good. All right. In which case, let me stop recording.